Yes, I'm Mike Volkos. I'm an associate controls engineer for Cato. I graduated from Mankato State University about a year and a half ago. I've been a NEDEC employee here for a little over 3 years, and the main task I have while working here is designing control panels for our generators mostly.
And I'm Chris Fleming. I'm a controls engineer intern. I'm currently attending Minnesota State University here in Mankato, and I've been a NEDEC employee for a little over 2 years. And one of my primary roles here is programming voltage regulators for commercial use. Now, to get things started, I'd like to go over a few quick definitions of terms that we'll use throughout the presentation. The first one is prime mover. Prime mover is the term used to refer to the device that is used to spin the generator's rotor. This includes devices like diesel engines and electric motors. Closed loop system. A closed loop system refers to a control system that is able to monitor the output and compare that output to a control signal and find the amount of error present. Then it uses that information to compensate for error. So basically, it's got a feedback loop. An open loop system refers to a control system that is unaware of the output and does not have a feedback loop. Reactance. Reactance is the difference in phase between voltage and current, and reactance occurs with inductive and capacitive loads, and we deal with a lot of inductive loads due to motors and transformers. And then I have this graphic here to kind of illustrate the difference. This red waveform right here is the voltage, and the green is the current that's in phase. So in purely resistive loads, the voltage and the current will be in phase. You see how these peaks line up right here? Now with inductive loads, the current will lag behind the voltage. So this axis is time right here, and the peak of the voltage happens here. The lagging current due to inductive loads happens here. And with capacitive loads, the current leads the voltage. So the peak of the current is right here, and the peak of the voltage is right there for capacitive loads. Now, programmable logic controllers. Programmable logic controllers are basically computers that can be used to control and monitor generators. These controllers have digital and analog inputs and outputs to send and receive information about the generator for the purpose of monitoring and controlling it. And now moving on to voltage regulators. The two different types of voltage regulators are analog and digital. Analog regulators are a simple and inexpensive way to control generator dynamics. They come equipped with little to no protection, but they do get the job done. Digital regulators are great for providing protection for the generator and by providing a robust way to control the dynamics of a generator using a full PID compensation. The job of a voltage regulator is to control the output voltage of the generator by changing the amount of excitation. This is true for just maintaining a steady state voltage when no load is applied, and also true for being able to adjust excitation in response to load being applied and load being removed. And digital AVRs have the added capabilities of providing a lot of protections. Now let's get into some finer details about the similarities and differences between analog and digital. Analog regulators will typically have 1 to 3 phase voltage sensing. They have the ability to control the paralleling between other generators or the power grid. They typically have a potentiometer for adjusting the set point for output voltage. They may come equipped with a simple stability adjustment with a partial PID controller for changing the behavior when reacting to load. They might have an over-excitation limitation for protecting the generator. They typically have frequency compensation for adjusting to a low frequency scenario, otherwise known as volts per hertz or low frequency. Because very large loads suddenly being applied to the generator might cause a lot of stress to the prime mover due to the additional torque being added to the rotor, the regulator might come equipped with a load acceptance module to help reduce some of that stress. The biggest advantage to an analog regulator is the cost savings. They are cheap because they do the basic minimum to keep the generator running properly. That comes with the caveat that they offer little to no protection for the generator. Digital regulators, on the other hand, essentially do everything that an analog regulator does, but also has ways of protecting the generator and also logging data associated with the generator's operations. Digital regulators come equipped with a more in-depth stability control, known as PID compensation. This allows you to adjust 3 different set points to really hone in on generator stability. Digital AVRs can be connected for redundant operations, so in the event that one AVR fails, the other can take over in its spot. RTD monitoring, auto tracking, and programmable logic functions are common features offered on digital AVRs. The biggest advantages digital regulators provide are the integration with programmable logic controllers, often used in control panels, and they have many programmable protections. Cost and complexity are notable disadvantages. So here we have a simple block diagram to illustrate the voltage regulation process. The voltage regulation process is going to start off with the regulator sensing the voltage at the generator output. So these sensing lines right here will let the regulator know what the voltage is at the generator output. Then the voltage regulator will decide, is that at the set point of the generator or is it not? So if we're trying to regulate the generator at, say, 480 volts, the first thing the voltage regulator is going to do is check to see, are we at 480 volts? If we're not at 480 volts, then the regulator is going to have to decide to lower or raise the excitation. And then that will change the output of the generator. If it needs to raise the excitation, it's going to need to pull power from an input power source. This input power source can be a number of different things. Throughout this presentation, we're going to stick with the example of a PMG, or otherwise known as a permanent magnet generator, which would be a permanent magnet generator that's on the end of the rotor of the generator, and that will be used to power the regulator for the excitation purposes. Now let's get into some more finer details of the voltage regulation process. So like I said, the process starts off with the voltage regulator sensing the voltage that's present at the generator's main stator right here. It's going to see, is the AC voltage here at the proper set point that you have the regulator set to? If that's not the proper set point, then the voltage regulator is going to have to change the excitation. If it needs to raise the excitation, it's going to need to pull power from a power source. In our example, like I said, is a PMG rotor, a PMG that is on the rotor of the generator. It will pull power from this PMG output, and it will have to rectify that into DC. Once it's rectified the DC, it will go into the stator of the exciter. And then the rotating rotor right here will pick up that voltage from the magnetic field produced by the stator, and it will be in the form of AC voltage. And now that AC will come down the rotor, and it'll have to get rectified once again. So it'll go through rectifying diode, this rectifying diode assembly right here, and then continue down the rotor in the form of DC. And this spinning rotor will create a magnetic field, and the main stator here will pick up the energy from that magnetic field, and it will start collecting voltage in the form of AC. And that is the end of the process, because the main stator is the output voltage for the generator. Now I'd like to talk a little bit about the control of the output excitation. So some analog regulators will have a stability and a response adjustments on their console, and it's basically a PI. But when it comes to digital regulators, it does have a full PID compensation, and you enter in numerical values for gains. So let's get in more to the PID portion of it. PID stands for proportional, integral, and derivative. I'm going to explain this block diagram here real quick. So first off, we have a set point, and this will be what we want the generator's output to be. So earlier I said 480 volts, we'll stick with that. So let's pretend for a moment that we want our generator to regulate at 480 volts. This set point right here will go into this summer, and the output voltage will be sensed in a feedback loop right here, and these two will be compared. It'll be looking to see, is this output the same as our set point? So is this output 480 volts? We'll see. Then after it compares those two, the difference in the two will become the error. And now I like to think of these three as three different workers, and each of these workers are observing this error in a different way. And don't worry, we don't have to do any math. These mathematical symbols are essentially there just to illustrate the idea. So these three are going to be looking at the error. The P, standing for proportional, is essentially looking at how large is the error in proportion to the set point itself. Are we way away from 480 volts, or are we somewhat near 480 volts? And the response will be in proportion to the disparity between the 2 points. The integral is going to take a sum of errors over time to understand the trend of the error. Basically, are we hovering around the set point, going plus and minus all the time, or is it, heading in one direction below the set point or heading in one direction above the set point? And then the D, standing for derivative, is going to take a look at how quickly the errors are changing. So are we rapidly approaching the set point, or are we slowly approaching the set point? Are we rapidly deviating from the set point, or are we slowly deviating from the set point? Then all three of these workers right here will communicate to each other, I guess you could say, and their output will be summed together, and that is what will control the excitation of the generator. So, like I said, P stands for proportional, and is typically represented by a KP, and the KP gain will control how large the response to the error will be. This setting has a major impact on transient response. I stands for integral and is usually represented by Ki. This parameter takes a sum of the errors to get an idea of the total amount of error occurring and the trend of the error. This gain is mostly used to correct steady state error so that when the generator is sitting at the rated voltage, it doesn't just keep fluttering around the set point. And then D stands for derivative and is usually represented by Kd. This parameter calculates the change in error over time to get an idea of how quickly the changes in error are occurring. This gain helps to control the overshoot in voltage when responding to load changes, otherwise known as transient response ringing. And I've added one more graphic here to further illustrate the process of dynamics control. So this axis right here is time, and this axis is voltage. So we're going to pretend for a moment that this is a response to a transient. So we just applied a huge amount of load. So we're coming from this is the set point. So we were at the set point, and now we hit a huge load, and so we're coming back up to rated. This initial portion of the ramping back up is mostly going to be governed by the P setting. So proportional is going to take us back up towards the set point. And then when we start approaching the set point, that's where the derivative is going to kick in. It's going to see that we are getting closer and closer to the set point, and it will work to try to make sure that we don't way overshoot the set point. And, a lot of times you're going to have a little bit of overshoot, but the derivative is there to mitigate as much as it can the overshoot when you're approaching the set point again. Then we have here some fluttering around the set point, and that's what the integral is going to try to take care of. It's going to see the fact that we're hitting a plus and a minus, and we're fluttering around the set point, and it will work to smooth out those bumps so we get a steady flatline output at the set point. All right, so let's continue on to digital voltage regulator modes. There's a lot to choose from, but I'm going to hit the main three that are typically used and talked about. First off, automatic voltage regulation is more or less the desired regulation mode because it utilizes a closed feedback loop, which is ideal when reacting to load changes. Field current regulation mode is usually a fallback mode for situations like loss of sensing, because this mode does not need to sense the generator's output. This mode will work to just maintain a fixed exciter current no matter what's going on with the load change. Because the regulator can be aware of how much current it's outputting, it doesn't need to look at the voltage at the output of the generator. So it will just maintain a fixed current output. And then same with the field voltage regulation mode. It's essentially the same thing as field current regulation, but instead it works to maintain a fixed voltage at the exciter. So here's a Nidec D550, and we're going to go through the inputs and outputs of a typical digital regulator. Starting off with input power. So this is where you would connect the PMG from our previous example. This is where it's going to pull power for the use of excitation. And then we have the field output. These are going to be the DC outputs that send current to the exciter for changing the excitation power for the generator. Board power. This is what is used to power the inner circuitry of the board. In our example here, the D550 takes from 24 to 48 volts DC to power the circuitry of the board. Some regulators will pull DC power off of the input power, but that's, depends on what device you have. Voltage sensing, this is where we would connect the output of the generator to sense what voltage there is at the output. Sensing CT inputs, this is what we would use to sense the current that is leaving the generator. This would be used also for paralleling units. RTD inputs, this is what we'd use if we wanted to monitor temperature at different points in the generator. The USB port is what we connect to upload and download programs to the regulator, and we can also use that to monitor different behaviors of the regulator. Digital and analog inputs and outputs. This can be used for a lot of different things, and it is a really handy tool for communicating and integrating with PLCs, because you can have the PLC control a number of different parameters through the analog and digital inputs and outputs. For instance, you could change the voltage set point. You could change the voltage regulation mode. You can have different faults be output to your PLC so that your PLC can be aware of the fact that there's an overcurrent fault or an overvoltage fault or an underfrequency fault. So it's really great for integrating your control panel for your generator. The CAN bus is used as a serial output for monitoring different aspects of the generator and regulator. And then these indicators over here, typically a regulator will have several lights on the front for kind of like the most critical faults or voltage regulation or the regulation modes. For instance, here we have 4 red lights for 4 different faults. It's the under frequency fault, over excitation fault, and such. And then this yellow light here is just showing the fact that whether or not the regulator is currently exciting. Here's a couple different regulation modes that it would like to represent. And then the power on here is just going to show that the device is powered. And then the USB light here indicates whether or not you have a USB cable connected currently. So the 2 different generator configurations are island mode and paralleling mode. Island mode is when you have one generator that is producing power for one load. And paralleling is when you have any 2 or more generators sharing a load. Island mode typical uses are construction sites or backup power for businesses and homes. Paralleling can be used for grid power or redundancy in the event that you want to have generators that are ready to be backed up in the event that one of them fails. So from here, we're going to go into more in depth into the paralleling of generators. And at this point, I'm going to let Mike take over.
All right, so there are 2 ways to control the paralleling of units. The first one we will go over is reactive group compensation. This process requires that the generator has a CT monitoring the amount of current leaving the generator output. This is used to calculate the amount of reactance in the load that it is receiving. Based on this calculation, it adjusts the output voltage in response to load changes. The set point in the program allows for a set amount of voltage droop to occur when there is a reactance in the load, mostly used for inductive loads like powering a motor. The advantages are that there is no extra wiring and it is easy to connect. The main disadvantage is that the voltage set point can change. The next paralleling method is cross-current compensation. Cross-current compensation uses interconnect current transformers so that each generator can be aware of the amount of current each of the generators is putting out so that it can be sure it is sharing the load equally between generators. The main advantage is that the output set point will remain constant because the generator is able to calculate the power being output by each generator. The disadvantages include extra wiring that can get complicated. Also, the CTs need to be identical, or further calculation will need to be done to ensure that the current seen by other generators is compensated for. Lastly, the generators will need extra contacts inserted at the CTs so that the CT can be bypassed if the user wants to only use one of the generators at a time. In this section, the protections and limiters are going to be taken from the EasyReg Advanced software, which is a software used to configure our D350, D550, and D700 regulators. This graphic shows what the protection set points look like. The protections will have to be activated by a checkbox. The protections will have a delay period since we don't always want the fault to be activated immediately, because it is common for set points to be exceeded for only a short period of time and will be corrected within a reasonable amount of time. The fault threshold will be a set point either based on the percentage of the set point or the unit of the set point being monitored, like voltage, current, or temperature. In the EasyReg Advanced software, we have the added convenience of choosing what the regulator does when it sees a fault. It can be programmed to do nothing besides show a fault has been tripped. It can stop the regulation. It can go to field current regulation mode with the set point of either the shutdown current or the field current before the fault. The under excitation limitation measures the amount of reactance and compares that to the reactive capability curve to make sure the generator is not being under excited. This is one way to detect the loss of a field connection, and this curve will be referenced again later when we have our programming demo. Overexcitation limitation will limit the amount of current going to the exciter. This is necessary because the excess current can cause the exciter to overheat. The protection in this graphic allows for 3 levels of limiting. Each level selects an amount of current and the time allowed for that current to be present. This protection is quite important for generator protection. Stator current limiter is commonly used because limiting the amount of current output can be a critical protection device. This limiter typically allows for a prescribed amount of excess current because some of the users might want their machine to output more than rated current for a short period of time. One critical function of this limiter can be the short circuit protection. For the under frequency limiter, the knee setting selects the frequency at which the volts per hertz mode becomes active. Once volts per hertz has become active, then the regulator adjusts the set point based on how low the frequency goes. The slope setting determines how rapidly the voltage set point is decreased in response to a lower than nominal frequency. When the frequency of the generator decreases, this is an indication that the prime mover is struggling to provide enough power to keep the rotor rotating at nominal speed. The regulator reduces the voltage to decrease the amount of torque required to spin the rotor so that the prime mover can catch up. Generator over voltage and under voltage are used to protect the device that are pulling power from the generator. Some devices that are being powered by the generator might have specific voltage needs and might be sensitive to a large voltage fluctuation. Also, of course, these two protections are used to keep the generator in a safe running condition as far as maintaining rated set points goes. The user may also want to monitor the diode assembly that is in charge of rectifying the exciter output. The open and shorted diode monitor observes the harmonics in the field current, and the user sets a percentage threshold for when to activate the fault. The shorted diodes will cause a large percentage of harmonics to be present in the current that comes back to the regulator from the exciter. The open diode will cause harmonics to be present in the exciter current returning to the regulator, but it will be quite a bit lower. And this allows for the regulator to differentiate between open and shorted diodes. Now I'll show you where to find the information for determining the various set points used for a voltage regulator. The nameplate that comes with your generator provides a majority of the necessary information. The reactive capability curve should be available to you if you request it from the manufacturer. The manufacturer schematics should be available to the user by request if the unit did not already come with them. This is an example of a generator nameplate. Of course, not all generator nameplates will have the same information listed here, but I would expect them to at least have the following values, which are line-to-line voltage, frequency, power factor, PMG output voltage, PMG frequency, exciter full load current, and full load exciter voltage. The reactive capability curve shows the generator's ability to handle inductive and capacitive loads. The lines extending from the origin represent various power factors. For our purpose, we will focus on inductive loads, which is represented by the bottom half of the curve. The AVR uses this curve to monitor under voltage conditions. The way we input this information is by recreating the curve in the AVR program so that it knows the reactive capability of the generator. The generator time constants should be available by request to the manufacturer. Some programs allow the user to enter these time constant values, and the program will auto-tune the PID gain for the generator as a starting point for the PID. If the output voltage of the generator exceeds the rating of the sensing terminals on the voltage regulator, then it is necessary to use a voltage transformer for sensing. In the event that you have to use a transformer, it is necessary to find out what the ratio is so that the regulator knows what voltage it is actually seeing at the output. A current transformer is necessary if the user wants to monitor the output current of the generator or for paralleling generators. Typically, regulators will have either 1 amp or 5 amp input from the current transformer, so the user will need to have a current transformer that has a 1 or 5 amp secondary. The programmable logic functions provide an extra form of control over the generator's behavior. For instance, the gate at the top here, is an AND gate, and you could have this gate monitor two functions and have the programmed output occur in the event that both of the inputs are true.
Okay, so I'm going to demo a voltage regulator program for a D700, and keep in mind that the software that's used to program a D700, this interface is the same. It's basically the exact same interface for the D350 and the D550. The only things that change are in accordance with the different features that they offered, but the screen looks the same, drop-down menu is the same, everything else is the same. So I have a generator in mind that I've basically made up a mock generator scenario, and I'm going to just start, putting in set points to just show you how my job works when I go to program a voltage regulator. So first off, essentially everything on this page is going to be able to be found on your generator nameplate. So for my generator, we're going to pretend that we have a generator that has a voltage output of 13,800 volts. The generator is 60 hertz. The power factor is 0.8. The rated apparent power is going to be 4302.5 kVA. And you can see here that it calculates these numbers for you. And this rated current right here is something we're going to have to pay attention to later on in this programming process. The pole ratio is the ratio between the exciter poles and the generator poles. And the regulator is going to be using this information for the diode fault monitor, because it needs to know what harmonics to look for when it's reading what harmonics are present in the current that is coming back to the regulator from the exciter. So in our situation, we have 24 exciter poles and 8 generator poles for a pole ratio of 3. Field inductor resistance in our situation is 8.68 ohms. Shutdown current, we briefly mentioned this earlier. This is a set point for the field current regulation mode that you can use if you have it set in one of the protections as the action after fault. So for now, we're just gonna leave that at what our rated exciter current is. And then here's our field rated current, which again is gonna be 6.63. So now moving on, you can either choose to hit the next button, which will just take you linearly through the menus, or you can just hit this drop-down menu and skip around to whatever menu you want to go to. So next, we're going to hit up wiring. Wiring is going to take care of all of our transformer needs. As we mentioned before, if the output of the generator exceeds the voltage, the rated voltage for the inputs to the sensing on the regulator. In our situation, our regulator is limited to 540 volts for sensing, and our generator is 13,800 volts. So that far exceeds the rating of the regulator. So we're going to have a transformer at the output. So our transformer, we're going to say, goes from 13,800 down to, I don't know, let's say 120 volts. So this is going to let the regulator know that there's a transformer between the output of the generator and the regulator itself, so that it knows what it's actually seeing for an output voltage. Generator CT, this is going to be necessary if you want to monitor the current leaving the generator, and it's also going to be necessary in any paralleling process. So our output current is 180 amps, and the secondary is going to have to either be 1 or 5 amps, and we'll leave it at 1. There's a few other transformer options, not terribly common. They're more of a specific scenario, so I'm just going to keep moving forward with a typical generator. So if we wanted to parallel in the cross current mode, we would need a cross current CT as well, which would have to be 180 down to either 1 or 5, and we'll leave it at 1. And then there's a couple other options here. One's for redundancy, second D700. So this is what we would use if we wanted to have a redundant D700. And then here is where we would start to configure the temperature probes. So you'd select which RTD type you're using, and so on. So this is the reactive capability curve, and what we're going to do is we're going to recreate the bottom half of that reactive capability curve. And this is the same curve from our presentation. So what we're going to try to do is we only have 5 points to choose from. And we're going to pick the 5 points that best illustrate the characteristics of this curve. The two first points that we would pick would be the origin here and the crossing the axis over here. So that's 2 of our 5 points. And I usually like to pick a point near the 0.8 power factor, because that's the power factor we're going to be regulating to. But in this situation, we do have kind of a corner on this curve right here. So I'm going to pick a point at this corner, and then we have 2 more points left over to choose. So I usually pick about a midway point around here and another midway point around here. And in this scenario, we're not entering in actual unit values of KVA, we're entering per unit values, so a percentage of the rated KVA. So I'm gonna just quickly move through these set points. So we're gonna have 0%, and then negative 67%, and then 72%, and then negative 54%, 86%, negative 50%, 38%, negative 20, 100, and 0. So we'll take a look at this curve again. I know it's kind of like backwards and upside down when it comes to relating these two curves, because this is the bottom half over here and it turns out to be the left side. But anyway, if you can kind of look here, you can see that this curve right here is pretty similar to this top half over here, as similar as you can be with only having 5 points to choose from. And then this portion of the curve right here is illustrated by that. Yeah. So we'll move on. Next step in the process is choosing overexcitation limitation. So this is what is going to limit the current that is going to the exciter. And we will want to use this setting because excess current in the exciter can cause overheating. It can also cause, an over voltage or over current in the generator itself. So we don't want to overexcite the generator. So this green portion right here is going to come all the way up to 100% of the set point. It doesn't actually label the set point. This is not our full load current. Our full load current ends right here, and it's actually 6.63 amps. So this can be held for an indefinite period of time. It extends on forever. Now this yellow field will be the next portion, and that will extend from 100% to 110%. So whenever you're in this region, it will extend for, we have chosen 3,600 seconds. And these are essentially arbitrary values, by the way. You're gonna have to decide on your own what kind of protection you want, because it's really a case-by-case scenario as far as how much you want to limit your exciter. Anyway, so this yellow region extends on for 3,600 seconds or 1 hour. And then after it reaches that period of time, it will ramp back down to rated current. This orange region will extend from 111% to 150%, and we have a duration of 120 seconds. So when we reach the 120 second mark, it will slowly ramp back down to your next region and then continue to ramp back down to rated current. This red region we have set from 151% to 200% with a duration of 10 seconds. And again, once we reach 10 seconds, it'll just slowly ramp all the way back down to rated current. Next is the stator current limitation. So this will limit the current that is actually leaving the generator, the current that is going to your load. And it's the exact same functionality as far as the different zones work. We have our yellow that goes to 110% for 3,600 seconds. We have our orange that goes to 150% of rated for 120 seconds. And then we have our short circuit protection for 300% for 10 seconds. And it's the same process. Once you reach the time markings, it will just slowly ramp all the way back down to the rated output current. Here's the protections pages. As you can see, there's a lot of them. So I'm not going to go over all of them. These, again, will have to be chosen by the user. It really just depends on what you want to protect. And you also have to pay attention to whether or not there's already a control panel in your unit. There could already be protections that you have, various other protections that are either done by the PLC or circuit breakers, those kinds of things you have to take into account, because you don't want to have too many redundant protections that might cause problems with troubleshooting when you do have a generator malfunctioning. But I will quickly point out the process of selecting these points. I know Mike already went over it, but I'll do a quick recap. You'll have to press the activation to activate the fault, or to activate the protection. And then you'll have a delay period of time, because sometimes, if it's over voltage, we don't want it to trigger every time we go, 1 volt over the set point. So we'll set up, say 10 seconds to make sure that it's actually a real over voltage scenario. And then this percentage set point is stating what percentage of the of the rated voltage you're willing to exceed. Oh, sorry, this is actually under voltage. But anyway, so it's stating how far away from the voltage set point you're willing to go. And then this is the delay period. And then this is the actions list. You can choose to have no action. Even though it says no action, there will actually be a red indicator up here that will say under voltage. So when you have no action, there will still be a warning. There's stop regulation, which shuts down excitation. And then these two settings right here will take you into a field current regulation mode. The shutdown current would be the set point that I showed you on that first page, or you could go to field current regulation before the fault. So it'll pay attention to how much field current was being output right before the fault was initiated. And this will take you back to field current regulation mode at the set point of that current. And let's move on to voltage regulation mode. So with the D700, the startup has to be activated by digital input. So we'll select D1. As you can see, there's a lot of digital inputs we can choose from. And then this is the soft start duration. Just depends on how long you want it to take to get up to rated voltage. So we set it for 5 seconds. As you can see, it rather quickly ramps up to rated voltage. You can set it for 25 seconds. Have it take quite a while to get up to rated voltage, and that's something that'll have to be chosen by the user. Voltage regulation mode, you can set this to be always enabled, or you could have it triggered by a digital input, or you could say none if you're intending to use a different voltage regulation mode. This sets your different limits for how far you can manually adjust the set point. The actual set point of the rated set point will always be 13,800, but if you want to temporarily change it to a different voltage, you can set a limitation allowing you to manually adjust it. In this scenario, we could manually adjust it from anywhere from 90% of rated to 110% of rated. You can type in that value right here if you want to change it by connecting a USB cable like we currently would be. You could change it here manually with a computer, or you could change it with an analog input. This would be either a 0 to 10 volt, plus or minus 10 volt, 4 to 20 milliamps. It would be controlled with a potentiometer, or it could be controlled by an analog output of a PLC. And then we also have the digital way of changing the set point. You would choose the lower and raise digital inputs, and this would lower the voltage. This would raise it, and this controls how much it raises and lowers it every time you press the button. And then this is the volts per hertz or under frequency mode. This initiates the mode. So if we're at 60 hertz is our rated, so I would typically put that at 58 volts. So that if we dip below 2 volts below, if we dip below 2 hertz below rated, then it will activate this volts per hertz slope, which is represented up here. And this shows how it's going to lower the set point based on frequency. This is frequency right here. So as you can see, the slope would be initiated at 58 volts, and the slope indicates how quickly it will lower that. So if we change it to 5, it rapidly reduces the voltage. And this is a device that's supposed to help relieve some of the stress from your prime mover. And then here's some more voltage regulation settings: the reactive droop compensation percentage for paralleling, the cross current voltage set point percentage for cross current paralleling. And then there's some more engine help settings over here. PID settings, these are the 3 different gains. And the way to set those is basically depending on how your generator is reacting. I've had pretty good luck so far with these initial settings, but if they're not working for you, then you can refer back to the previous slide and check to see, are you overshooting, or are you just not responding fast enough, or are you fluttering around the set point, and just kind of pay attention to the way the generator is reacting and then change the set points accordingly. And then lastly, I'll just go to this inputs and outputs section. This is where you can manually change what the digital inputs, digital outputs, analog inputs, and analog outputs are going to be associated with. And as you can see, there is actually quite a long list of things that you can have changed by this digital input. And then you can choose to have it either active high or active low, which means that it would be active at 0 volts or active at plus 5 volts. And then again, there's a pretty long list of analog regulator or analog inputs that can change a lot of different things. Yeah, so obviously I could go a lot deeper into this, but I'm hitting kind of the high points of what a typical situation looks like. There's obviously way more specific situations, and those, will have to be taken care of as they go.